This chapter will give you a general overview of the most common propulsion and manoeuvring systems used today. A ship's manoeuvring characteristics are directly related to her hull form. Optimal performance depends upon the hull shape in conjunction with engine power and the propeller and rudder systems. Most ships are still equipped with traditional single fixed propeller and single rudder, designed for getting the ship from A to B as economically as possible. This often represents a challenge to the ship handler with reference to manoeuvring in confined waters. In order to achieve a better balance between manoeuvrability and economy, some vessels are equipped with propeller and rudder systems that differ considerably from the traditional systems. General information about some of these new systems will be given later in this chapter. The diesel engine is very widely used, as it tends to be the least expensive to run. Low-speed diesel engines operate directly onto the shaft. Maximum speed RPM is in the range 85 to 130 RPM. The ship handler must remember that difficulties can be experienced in starting the engine when still making a lot of headway. This is because the propeller will be trying to turn in the water stream, and because of the direct drive, the engine tends to turn in the forward direction. Another important thing to remember is that sometimes there might be a limited amount of start air available, i.e., too many starting orders during a short time interval may empty the start air reservoir, making engine start impossible for some time. Medium and high-speed diesels are popular arrangements in smaller vessels, ferries, car carriers and other special ships. One or several engines drive a shaft through a gearbox and clutch. The engines are normally operated from the bridge and are very responsive, and like their low-speed relatives, can develop almost as much power astern as ahead. But, of course, the application of this astern power is less efficient, as ships' hulls, propellers and rudders are usually designed to work in the ahead direction. The steam turbine is often found in large ships and on ships where high speed is required. A turbine ship, while being smooth-running and more reliable in the mechanical sense, has one major drawback. From the ship handler's point of view, its response to control orders for change of direction of shaft rotation are slow. Thus, when manoeuvring a turbine-driven ship, each movement must be carefully planned. Controllable pitch propellers are very practical because by modifying the pitch, they allow for thrust optimization under different load conditions. With the controllable pitch propellers, the user can modify the pitch, normally by means of a hydraulic mechanism. Click on each hotspot to learn more about CPP. Pitch is the distance a propeller drives forward for each complete revolution, assuming it is moving through a solid element, just like a wood screw does. When using a CP propeller, the main engine has to be clutched in, so the propeller is continuously turning, usually at quite high revolutions. As it is neither practicable nor economical to run an engine continuously at excessive high RPM, it is important to have some kind of combined control over both RPM and pitch, so that the pitch for slow speeds is balanced by a reduction in revolutions. On most ships, this is achieved by installing a combinator, which automatically balances engine revolutions against propeller pitch, thus producing a saving in fuel and better propeller performance. To use a head power, a ship with CP propeller is not restricted to the old stepped progression that has been associated with fixed pitch propellers. Any speed can be selected by adjusting the combinator control to the required setting. It is also possible to set the propeller pitch for extremely low speeds, so when it is essential to proceed at very slow speeds, the propeller and rudder are still active, and steerage way can be maintained for a lot longer than usual. When low speed or stop are demanded, the blades of the CP propeller are set with a very fine angle and pitch. If the ship's speed is too high and does not already match the propeller speed, the flow of water through it will be restricted, and turbulence will develop behind the propeller, which will also have an adverse effect upon the rudder. If the ship's speed is not reduced slowly and progressively in much the same way as a large, directional, unstable ship, the rudder will be shielded, and the steering may become erratic or poor. One of the most common concerns mentioned by many navigators and pilots is the uncertainty as to which way the bow will cant, if at all, when a CP propeller is put astern. To answer this question, it is necessary first to know which way the propeller is turning when it is viewed from astern. The majority of the CP propeller is left-handed, i.e. they move in an anti-clockwise direction. The effect, however, is similar to a fixed-pitch right-handed propeller working astern, i.e. the bow may cant to starboard. It is important to note that the transverse thrust on some ships with CP propellers may be weak and unreliable due to vortices or turbulence around the propeller blades. It is therefore advisable to exercise some caution when anticipating the effects of stern power on some CP ships. Many vessels, ranging from tugs to large ocean-going ships, are equipped with ducted propellers. A shroud or duct is a tube or tunnel-like construction with the propeller inside. The forward end of the duct has a larger diameter than the aft end. The increased power comes from the propeller constantly drawing a mass of water into the duct, which then has to be forced out through a smaller aperture. The main advantages which can be expected of the ducted propeller are: more output power from the propeller, reduced propeller wash to a smaller arc, thereby reducing erosion of canal and river banks, better steering, especially at low speed, better turning characteristics. Conventional rudders, found on thousands of ships worldwide, represent a compromise between economy and necessity. Conventional rudders normally function satisfactorily for normal steering and course change requirements in open waters. The basic conventional rudder is efficient up to maximum 45 degrees. At higher angles, the rudder is not capable of maintaining a smooth water flow across both sides of the rudder, and the rudder stalls, i.e. loses its effect. If the rudder has its entire area after the rudder stock, then it is unbalanced. A rudder with between 20 and 40% of its area forward of the stock is balanced. Most modern rudders are of the semi-balanced design. This means that a certain proportion of the water force acting on the after part of the rudder is counteracted by the force acting on the forward part of the rudder. Hence, the steering gear can be lighter and smaller. There are several types of rudder designs. Click the hotspots to see the 3 most common types. This is the most used rudder type on ferries and smaller ships. The spade rudder provides good maneuverability. This type of rudder is most commonly used on bigger ships. It is not as effective as a spade rudder of the same size. The heel rudder is supported with bearings on the top and bottom, providing an endurable rudder construction. Conventional rudders are somewhat restricted when it comes to maneuverability at slow speed in confined waters. Several manufacturers have developed more efficient and advanced rudder systems the last 2 or 3 decades, and quite a few ships are now fitted with modern and more efficient rudders. Click the rudders to see some examples. The flap rudder is different from a conventional rudder in that it utilizes an additional flap on the trailing edge for steering. This allows up to twice the steering power compared to a traditional rudder, translating into a much more maneuverable ship. The rotor rudder is essentially a conventional rudder, but with the addition of a rotating cylinder mounted vertically on the edge of the rudder. The purpose is to smoothen the water flow at high rudder angles and thereby improve ship turning performance. The purpose of the T-rudder is to combine the advantages of the flap and rotor rudder in order to get the best possible rudder performance. The performance is indeed excellent, but unfortunately the price is high. Not many ships invest in this excellent rudder system. This is an alternative design to the flap rudder. The shape of the rudder is such that it can be turned up to 70 degrees and still retain excellent performance. The forebody of the rudder is elliptical in shape, but runs into a rear body section which is concave. Expected turning performance with flap, rotor and T-rudder systems. This diagram shows the expected increase in turning performance for a ship equipped with a modern flap or rotor rudder system. As can be seen from the diagram, considerable turning improvements are obtained. Special rudders deploying up to 70 degrees are used in much the same way as conventional rudders. When used in combination with a good bow thruster, it is possible to develop outstanding lateral motion. Care should be taken not to move with too high speed, as this may damage the rudder system or result in unnecessary wear and tear. Some systems don't allow a rudder angle of more than 35 degrees when the speed is more than 5 knots. This system is totally different from all other rudder systems, both in design and operation. The most unusual but essential feature of this system is the propeller, which even though it is fixed pitch, is constantly running with the engine permanently on ahead revolutions, normally in manoeuvring speed full ahead. Immediately astern of the propeller, in place of the conventional rudder, are 2 schilling rudders, each of which can rotate through a total arc of 145 degrees. The rudders do not act independently of each other, but are instead synchronized to work in harmony with each other in response to a single joystick control on the bridge. The twin schilling rudder system, with its constantly running propeller, seems a little strange at first. However, most officers, after a short period of instruction, appear to get the feel for it relatively quickly. In this diagram, you can see different joystick positions and corresponding rudder positions. If the joystick is eased back from normal full ahead with the joystick in full forward, the rudders progressively open outwards, deflecting the propeller's wash or drive and thus reducing the ship's speed. To obtain stern power up to the equivalent of full astern, the joystick is pulled right back until each rudder has rotated right around to 105 degrees, thus closing the gap between them. The propeller wash is then deflected forwards and works in much the same way as the reverse thrust of an aircraft's jet engines when it is deployed to stop the aircraft after landing. Study the diagram carefully to understand how the twin schilling rudder system works. The conventional propeller and rudder arrangement has been around for a long time. The propeller can be designed to turn clockwise or anti-clockwise. The position of the rudder, which normally lies in the propeller slipstream, is critical with regard to cavitations as well as efficiency. Conventional rudders normally have a maximum rudder angle of about 35 degrees. Generally speaking, a ship with a right-hand turning propeller can be expected to have slightly smaller turning radius to port than to starboard, and vice versa for a ship with left-hand turning propeller. Conventional designed twin-screw ships are normally designed with a right-hand turning starboard propeller and a left-hand turning port propeller, and equipped with 2 rudders, one behind each propeller. The reason for making the outward turning propellers is twofold: reducing cavitations and taking greatest benefit from the transverse thrust. The essence of good manoeuvrability of twin-screw ships is not the result of one factor alone, but rather several factors combined. These factors are the rudder configuration, the effect of torque, the effect of transverse thrust, the pivot point, the turning ability, a competent ship handler. In order to make the turning manoeuvres accurate and predictable, several modern autopilots have steering modes for executing and control of turns with preset turning radius or fixed rate of turn. In confined waters, the simplicity of the geometrical shape of the circle will ease the navigation and the control of the actual track. Today, when documentation of proper route planning is an IMO requirement, and more ships are equipped with ECDIS and advanced autopilots, even turns in open waters should be planned and executed in an optimal way. Click the waypoint, course and track mode buttons on the autopilot to see the difference between them. When turning with constant rate of turn, the radius may not remain constant due to speed reduction during the turn. However, if the turn is made with very low rate of turn, for example 6 degrees per minute, the speed loss is next to nothing. Low constant rate of turn setting on the autopilot is most useful on passenger ships, ferries and other ships operating in good weather, with stabilizers inactive in order to avoid drag and save fuel. A low rate of turn setting during a course change avoids banking the ship, even with stabilizers inactive. In general, a low rate of turn should be used whenever possible, as this has many advantages seen from a safety, economic and comfort point of view. The mathematical formula for calculation of rate of turn is as follows. For practical use, the formula can be simplified as follows. If we know the rate of turn, we can rearrange the formula and get the turn radius. Exercise. Calculate the rate of turn for a ship with speed 20 knots and a turn radius of 0.5 nautical miles. You can use this calculator by filling in the numbers in the grey areas. Many ships are equipped with autopilots capable of following a preset curve based on turn radius input. Turning with a pre-planned fixed radius is recommended whenever precision track keeping is required during a turn. The following points should be taken into account when planning a turn using a fixed turning radius. Use largest possible radius. Establish the wheel over point as accurately as possible. 1 to 1.5 ships' lengths from the start point of the turn radius is a normal value for most ships. Estimate wind, current, shallow water effects, etc., and be prepared to adjust heading manually whenever necessary.